Hello, my name is Jared Skeens and welcome to the Zoom room. Today we want to look at Pure Math 3, Differentiation, Part 3, Parametric Equations. Now, what are parametric equations? Parametric equations are a little different from our normal algebraic equation where instead of putting y equals something in terms of x, we have both x and y measured by a third variable. Parametric means alongside measurement. Para is alongside, metric is measurement. So we have an alongside measurement. Now you saw the kind of an introduction, a step toward parametric equations in Pure Maths 1, where in changing rates, if you had a volume formula in terms of radius, then when you took the derivative, you added a dt to both sides. You divided both sides by dt. So you had the change of volume with respect to time. And then on the right side of the equation, you had the change of radius with respect to time. So you added in that extra differential, that third differential into it. So that was kind of a step toward parametric equations. So parametric equations then are your x and your y, instead of being related to each other, they're related to a third variable, which usually will be time, or it can also be an angle measurement, how they relate to your origin with respect to a changing angle. So here we have up here two equations, one for the value of x, one for the value of y. Again, your x and y create a coordinate that's on your graph, but they're measured now, in this case, with the variable t, which could represent time. And so you have x equals 2t plus sine 2t and y equals ln of 1 minus cosine 2t. Let's just let you look at the question itself so you can see what the Cambridge question looks like. Here's the code, Winter 19, paper 31, number 3, says the parametric equations of a curve R, and here we see them right here, which I have on the board, show that dy dx equals cosecant 2t. Okay, let's get back to the board. Now I want to make one clarification at the very beginning of the video, in case you're watching this video and maybe you're thinking that this is going to be about parametric equations. This is Cambridge question type. It's not really using parametric equations and applying them to a story problem or real life situation. This is more about derivatives applied to parametric equations. So if you think this video is going to explain applications of parametric equations, it's probably not the video for you. This is about taking derivatives and applying it to parametric equations, basically with thinking about slope, how we can get a slope application from parametric equations. So that's an important distinction that I want to make at the beginning of the video so that you're not watching and waiting for parametric applications. We're actually doing derivative applications. Okay, so show that dy dx equals cosecant 2t. And again, as we get into these more lengthy line by line problems, in this video, I've already done the work. So instead of focusing on the algebraic steps, which if you're already in Pure Math 3, you already should have pretty sound algebraic skills. So instead of just working those with you, I want to focus on the mental aspect. Really, half of it is mental, understanding what it is you're looking for, what it is that you're trying to do. You should be able to understand the algebra at this point. So What we're going to do first is just do the derivative of our x and our y separately. So the derivative of x becomes dx. Now notice, because these are explicit equations, not implicit, I don't follow the differentials all the way through. I just go ahead and put dx dt because these are already explicit equations. So dx dt equals the derivative of 2t is just 2. The derivative of sine is cosine. You don't change the argument, but you do have to do the derivative of the inside. So first you're doing the derivative of the trig function, then you're doing the derivative of the argument. So that's where this 2 out in front comes from. The derivative of 2t is times another 2. Then we have the derivative of y, and the derivative of ln is 1 over the argument. 1 over argument. The derivative of ln x is 1 over x. So 1 over the argument. Then we have to do the derivative of the argument, which the derivative of 1 is of a constant is 0. So now we have to do the derivative of the trig function. The derivative of cosine is a negative sign, so the two negatives cancel. And again, it doesn't change the argument. Then you have to do the derivative of the inside or the argument of the trigonometric function. So you have the argument of the logarithmic function. Now you have the argument of the trigonometric function. So cosine is a negative sign, doesn't change the argument. But then you do the derivative of the argument, and that gives you the 2 again on the outside. Now, to take these parametric derivatives and put them together to create a slope of the graph, what we're going to do, slope is the change in y over change in x. When you divide by a fraction, because this is a complex fraction, so you need to invert and multiply. Just a note here, pay close attention to your major division bar. Not all division bars are created equal. And so you can tell by the length that you make them. In other words, you need to clearly distinguish your numerator from your denominator. In this case, the numerator has a fraction and the denominator has a fraction. Therefore, it's a complex fraction, and you invert and multiply the denominator, meaning you need to clearly distinguish what elements here are your denominator. Invert and multiply. At this point, this is referred to as the chain rule, where these differentials are lined up so that the dt's cancel out by using the chain rule, and that leaves us with dy dx. Change in y over change of x is our slope. So this is just kind of a brief explanation of what we're doing here. We're using the chain rule to put these two different derivatives together in order to end up with a slope equation. So the dy dx, we put the dy dt on top, which is the 2 sine 2t over 1 minus cosine 2t. Over, this is our major division bar here. I used a different color to distinguish it. Preferably, you should make it longer than the other division bars. Then on the bottom, we put our dx dt, which is just 2 plus 2 cosine 2t. I factored out the 2 and made it 2 times 1 plus cosine 2t. Notice I made another fraction and put it over 1, because this is a complex fraction and we need to invert the denominator. So to invert it, it kind of helps to make it a fraction over 1. That way when you flip it over and multiply, you get 1 over the 2 times 1 plus cosine 2x. So what we're inverting is this part, not these two here. So that's why you need to distinguish your division bars carefully. So this is not the denominator, it's this that's the denominator. This is what's getting flipped over. This is all the numerator. Once you have that, you should see that this 2 can then cancel with this one over here because we have divide against multiply. So those are opposites. So the 2's cancel out there. And that leaves us with sine 2t over 1 minus cosine squared 2t. Now, where this 1 minus cosine squared 2t comes from? That's this times this over here. You should recognize this as a difference of squares. A difference of squares. A 1 minus cosine 2t and a 1 plus cosine 2t. Those are conjugate pairs. They create a difference of squares, meaning when you do your smiley face method, when you do your expansion method, smiley face or FOIL method, whatever method you were taught, the inner and the outer, or the nose and the mouth, cancel out. So all you're really multiplying are the first terms and the last terms. 1 times 1 is 1, and a negative cosine 2t times cosine 2t is a negative cosine squared 2t. Like I said, the inner ones cancel out. Your negative cosine 2t and your positive cosine 2t cancel out. So you're just left with this here. Then you need to recognize this here as an identity. This is your Pythagorean identity. 1 minus sine squared plus cosine squared equals 1. So 1 minus cosine squared equals sine squared. Of course, your argument does not change. And so you use the Pythagorean identity. Then you have a single power of sine 2t on top. You have a squared power of sine 2t on the bottom. So one of those cancel, leaving you with a single power in the denominator. And again, you have an identity. This is your reciprocal, which we learned back a few videos in the trigonometry section. The reciprocal of sine 1 over sine is cosecant. So we use our reciprocal function cosecant 2t, and that is what we were asked to show. So the nice thing about a show is you know what answer you're aiming toward, and then what you need to do is, of course, derive both your x and y. You need to apply the chain rule to get the dy dx, and realize that you are basically simplifying your slope equation, or the equation that will give you value for slope at any given point on the graph that is defined by these parametric equations. Okay, so that's our first look at it, and let me set up the second problem. Okay, let's look at our second question here. And here's the code up here. Parametric equations of a curve are x equals t squared plus 1, y equals 4t plus ln of 2t minus 1. Express dy dx in terms of t, so basically just find the derivative. Then there's a follow-up question. Again, remember I said that we're really applying derivatives to parametric equations instead of applying parametric equations to something else. Find the equation of the normal to the curve at the point where t equals 1. So the normal to the curve, you learned this back in Pure Maths 1. At t equals 1, give your answer in the form of ax plus by plus c equals 0. So the equation of the normal is a linear equation, and they want the form ax plus by plus c equals 0. Okay, let's get back to the board here. Here's our two equations. First, let's express dy dx in terms of t. So we take the derivative of both. The derivative of our x equation, dx dt, equals 2t, and then there's the derivative of plus 1 is just 0. So all we have for this one is 2t. The derivative of our y equation, dy dt, equals, so the derivative of 4t is 4, plus the derivative of a ln is 1 over 2t minus 1. And then don't forget the derivative of the inside, and the derivative of 2t is times 2. So the derivative of your logarithm is 1 over and then the derivative of the argument times 2. Then, because we have two different terms here, we want to combine them, get a common denominator. That's why I put over 1. So our common denominator is 2t minus 1. Multiply the top here by 2t minus 1, and we get 8t minus 4, plus the 2 that's already there. And now we can do our dy dt divided by dx dt. So this becomes 8t, combine that, you get minus 2 over the 2t minus 1. That's the numerator. The denominator is 2t. I put it over 1 because we want to invert and multiply to get our chain rule. And if you just multiply across, you get 8t minus 2 over 2t times the 2t minus 1. This is your answer. It can be in any form. It's or equivalent. If you look at the mark scheme, it says OE or equivalent. You could factor out a 2 from the top and cancel it to have this. You could multiply the t through and have 2t squared minus t. So there's a lot of different variations that you can have here as long as it's, the same equivalent fraction. So this is the answer that you want there. And I actually take this one here because it's already got the factor of 2 reduced out. Now for the normal, remember normal has to do with slope. We just found slope, dy dx. If you remember from pure mass 1, your tangent line is what is tangent to your curve, and it has the same slope as the curve at the point of tangency. The normal then is perpendicular to the tangent. So if this is our slope at the point of the curve, it means it would have the same slope as the tangent line. So the normal is going to be the negative reciprocal because it's perpendicular. Normal is perpendicular to the graph. So we do the negative reciprocal, meaning you flip it over. So the t and 2t minus 1 goes on top, and we negate it, the negative reciprocal, and then the 4t minus 1 goes on the bottom. And we want to evaluate this at where t equals 1, whether t stands for time or whatever, it doesn't really matter. Evaluate it at t equals 1. It doesn't say the slope equals 1. It says at t equals 1. So we're going to evaluate it at t equals 1. So we plug 1 into the slope formula and we work it out and we end up with a negative 1/3. And in order to come up with an equation of a line, you need slope and you also need a point on the line. Well, your x and y coordinates are your point on the line. So we take that t equals 1 and we also plug it in here for our x and for our y to find out where a point is or the point that this normal is going through. So at t equals 1, 1 squared plus 1, so your x value is 2. Plug it in over here. You get 2 times 1 is 2. 2 minus 1 is 1. Ln of 1 is 0. You can work it out on your calculator. You'll end up getting a 0 for that part. So 1 times 4 then is just 4. So the 0.24 is a point on our graph that the normal line is going through. So we get that by plugging the t equals 1 back into our original parametric equations. Now from here on is just generating your equation of your line. So in this case, I used the point slope form. So y minus 4 equals a negative 1/3 times x minus 2. Distributed the negative 1/3, so negative 1/3 x plus 2/3. Multiply everything by 3 to get rid of the fractions. 3y minus 12 equals a negative x plus 2. And then rearrange it into this general form or standard form that they want. And so add x to the other side plus 3y, subtract 2, and you get minus 14 equals 0. Here's your equation of the line that is normal to this parametric equation at t equals 1. Okay, So that's our second one. I'll set up for the next one. Okay, let's look at our next problem. Says the parametric equations of a curve are x equals 1 cosine theta and y equals 3 theta minus tan theta. So notice our parametric variable is now the theta instead of the t. So be careful when you write your differentials, you're using theta, not t. Here's your code up here. It's from summer 17, paper 31, number 4. Also, we have a domain statement here because we're working with trigonometric values. Domain statement, theta is between 0 and pi halves. It says express dy dx in terms of tan theta. So we need to get our slope in terms of tan theta. Then it says find the exact y coordinate of the point at which the gradient of the normal is equal to 1. So we have a follow-up question. Okay, let's get back to the board. So one of the important things about the domain statement to notice is that it's in radians. So make sure you set your calculator to radians, although because we're dealing with exact values, you shouldn't actually have to use your calculator. But in case you want to verify something with your calculator, make sure you're in radian mode because the domain is in radians. So here's our parametric equations. Again, we're in theta now, not in t. So when we do our derivative, we want the derivative in terms of tan theta. So here's dx d theta equals, so here is our logarithm, which is 1 over x, or 1 over the argument, so 1 over cosine theta. Then you have the argument itself. The derivative of cosine is a negative sign, so that goes on top, negative sine theta. And you should recognize that sine over cosine is tangent, so we get a negative tangent theta. Then for the y value, we have dy d theta equals 3. So remember, theta is a variable, not a constant in this case. And so we get 3 minus, and tan theta, if you remember from the derivatives in our trigonometric section, that the derivative of tan theta is secant squared theta. It is in your formula sheet, so whenever you're doing derivatives or integrals, you should have that open in front of you for quick reference, but the derivative of tangent is secant squared theta. Then we want to find the slope, so we do dy d theta over dx d theta. So that's 3 minus secant squared over a negative tan theta. We've got this loose negative sign right here. So we're just going to multiply it through the top, take it out of the bottom, multiply it through the top. So that gives you secant squared theta minus 3 over tan theta. Since it wants it in tangent theta, you need to look at your identities. This is actually a derivative from your Pythagorean identity. It's in your formula sheet also. So you find your identity for secant squared theta, and you find that it's 1 plus tangent squared theta, and then you have your minus 3. So you clean this up, simplify it, and you get tan squared theta minus 2 all over tan theta. This is our derivative in terms of tangent. Then the second part of the question was to find the exact value. So remember, exact means no decimals. You keep pi, you keep radicals, whatever it is, you keep it, but you don't turn it into a decimal. And it said that it's the normal, the gradient of the normal was equal to 1. Well, like we saw in the last problem, normal is the negative reciprocal of the tangent, which has the same value as the slope of the graph. So we need to take the slope of the graph, and in order to get the normal, we need to do the perpendicular or the negative reciprocal. And so we negate it and flip it over. So here's the negative, and it's flipped over, tan theta over tan squared theta minus 2, and that gradient is equal to 1. Now we just multiply the tan squared minus 2 to the other side. You should recognize this as a quadratic equation with your squared power here. So get everything on one side and set it equal to 0. Tan squared theta plus tan theta minus 2 equals 0. Now you can factor that, the factors of 2 that subtract to give you 1. So you have tan theta plus 2 times tan theta minus 1 equals 0. So you see tan theta times tan theta is tan squared theta. 2 times negative 1 is negative 2. Positive 2 tan minus tan is a positive 1 tangent theta. Then solve each of those. Tan theta equals negative 2. Tan theta equals 1. Now remember, our domain statement is between 0 and pi halves, meaning we're limited to the first quadrant. Tangent is negative in the third and fourth quadrant. Okay, tangent is negative in the third and fourth quadrant, so we don't need those. And tangent is positive in the first and third quadrant, so all we need is the first quadrant. Now it says exact value, so if you do this in your calculator, if you do the inverse tangent of 1, it's probably going to give you a decimal value. So what you want to do is you want to draw up your special triangles, your 30, 60, 90 right triangle and your 45, 45, 90 right triangle. And look, where does tangent, opposite over adjacent, give you a value of 1? Well, if you're coming from the 45, your opposite over adjacent will give you a value of 1. So whenever you're working with exact values and you're working with trigonometry, use your special triangles to help you with that. So what you end up with is a 45. Now that's in degrees, so make sure you put it in radians. 45 degrees in radians is pi fourths. Remember, pi halves is 90, so 45 would be pi fourths. That's the angle that we want. And the question specifically asked for the y coordinate. So up here we have our equation for y, and all we need to do is plug in the pi fourths for the theta. So we have 3 times pi fourths minus tangent of pi fourths. And so we get 3 pi fourths minus 1 because tangent of pi fourths. We just kind of did the opposite of that right over here, is 1. And this then is our simplified or our exact y coordinate that fits this particular question. Okay, let's look at one more. We've kind of went through several of them, and I hope that you're establishing the mental aspect. The algebra part or the trig part, you should already be able to work through those parts, but mentally understanding those correlations like back to P1, normal tangent, those kind of things, those mental things to help you get through these problems a little bit more quickly, and then also be careful on the execution of your algebra, your trig identities, as well as the actual derivative rules themselves. Paying attention to when you have an expanded argument and you have to do the derivative of the inside, or if you have exponents to deal with. We'll look at one more problem. Okay, let's look at the last question for this video. And it says the parametric equations of curve are x equals 2 sine theta plus sine 2 theta and y equals 2 cosine theta plus cosine 2 theta, where theta is between 0 and pi. So notice again, it's in radians. Obtain an expression for dy dx in terms of theta. Then this follow-up part, which we'll have to get to a little bit later, also says, hence, find the exact coordinates, meaning both x and y, of the point of the curve at which the tangent is parallel to the y-axis. Tangent is parallel to the y-axis. We'll come back to that a little bit later. First, let's take care of the derivative part. So what we want to do, here's our two equations in x and y. We want to find dy dx in terms of theta. So dx d theta then is 2 cosine theta plus cosine 2 theta times 2. So don't forget the derivative of the argument. The derivative of the trig function is cosine, and then the derivative of the argument is 2. Same thing over here, dy d theta. Cosine is a negative sign. And then here again, we also have the trig function and the argument. So the derivative of cosine is a negative sine 2 theta, and the derivative of the inside is times 2. Then we want to get our dy d theta over our dx d theta. So negative 2 sine theta minus 2 sine 2 theta, factoring out the negative 2 in front, divided by 2 cosine theta plus 2 cosine 2 theta, again factoring out the 2 in front so that we can simplify this, get rid of those 2's. The negative is still there, so don't forget to add it. You can just put it in the front of the parenthesis, or you could distribute it through either way. This is our equation for that. Now, as we move forward, in the second part, it says find the coordinates, so x and y, we need to find our x and y, at the point which the slope is parallel to the y-axis. So if you're parallel to the y-axis, it means it's up and down. And if your slope is parallel to the y-axis, then that means it's undefined slope. And to get undefined slope means the denominator is 0. You can't divide by 0, and that's why it's undefined. But in your rise over run, you have all rise, and there's no left and right, no run. So the 0 is in the denominator. So what we want to do in the second part is to set the denominator equal to 0, because the slope is parallel to the y-axis, and the y-axis has an undefined slope. So this is the mental part that you have to be able to figure out what it means by the slope is parallel to the y-axis. Parallel means same slope. The slope of the y-axis undefined, meaning the denominator set equal to 0. So I'm going to really quickly erase this so I have a little more space. Okay, here we have our denominator set equal to 0. Okay, the denominator is set equal to 0. And now we have this right here, this cosine 2 theta is a double angle identity. So look that up. And for cosine, you actually have 3 different choices. You want to use the choice that keeps it in cosine, since you already have a cosine function here. So that's going to be the 2 cosine squared theta minus 1. That is your identity. So change it into that. Now you should recognize that you have a quadratic. So rearrange it in descending exponential order. Then you factor it. And after you factor it, you can then solve. So you get cosine theta equals 1/2. In which case, again, you're going to want to use your triangles. So cosine being 1/2 is your adjacent over hypotenuse. So that would be 60 degrees, which is pi thirds. Cosine theta equals -1. This is a quadrantal angle, and cosine is positive on the positive x-axis, negative on the negative x-axis. Cosine would be pi at -1, or the theta would be pi, so that cosine of pi is -1, and pi is not allowed in the domain. So don't forget to check your domain. There's no equal to there, so theta cannot equal pi. So the only value that we have is pi thirds. It wants the coordinates, the x and y value. So we need to come up to our original parametric equations and plug in the pi thirds for both the x and the y. Remember, you're using exact values, so you need to use your special triangles for that. And remember, for sine, sine is positive in the first 2 quadrants. So you end up with √3 plus root 3 over 2, get common denominator, you get 2 root 3 over 2 plus root 3 over 2, which is 3 root 3 over 2. For the cosine, you get 2 times cosine of pi thirds. Cosine of pi thirds is 1/2 times 2 is 1. This one pushes you into the second quadrant, and cosine is negative in the second quadrant. So you get minus 1/2. 1 minus 1/2 is 1/2. So your ordered pair then for this point is 3 root 3 over 2 and 1/2. So there we go with parametric equations. And more of what we're doing is actually applying the derivative and concept of slope with parametric equations. But so it does correlate a lot with previous material, both in P1 and the P3. So as always, thank you again for joining me, and hope to see you again the next time in the Zoom room.